Well, hello everyone, welcome back to Adrian's Digital Basement. On today's video, I'm going to be trying to pimp out this 286 motherboard a little bit. I recently worked on this motherboard on the second channel. I worked on a few different motherboards and I tested this one and it worked. But I want to actually improve it a little bit in this video because one of the odd things about this motherboard is it has 8 SIP sockets, single inline package. It's like a SIMM with pins on it. I don't like those because they're a pain to use and I don't have that many of them. So I'm going to try to swap out these SIP sockets and put in SIMM sockets. In addition, this thing has a broken slot, which I want to try to address. And it also has a missing crystal oscillator here. When maybe I can swap this out and then we can get some flexibility in overclocking the CPU a little bit. So without further ado, let's get right to it. So since the last time you saw this motherboard, I've given it a wash. It is nice and clean now. Now this is a cool 286 motherboard. It's 12 megahertz math coprocessor socket there. It uses this awesome chipset here where they condensed everything on a 286 motherboard down to this single chip. This chip came out around 1989, although you can see this motherboard was made in the 38th week of 1990 or thereabouts. Now I've worked with a lot of 286 motherboards over the years, and the one thing about this one which I found really interesting is, besides the fact that it's a nice compact size, it has 8 memory slots. And the chipset actually supports up to 16 megabytes of RAM, but unfortunately, you need a motherboard that has 16 slots, and there's one extra little chip they would have to add to, I don't know, multiplex some kind of a line or something like that. And then you would be able to have a full 16 megabytes right on the motherboard. What's cool about this particular chipset is it can run at 0 wait states, so that means you can take full advantage of the 12 megahertz speed of this CPU, and if you use fast enough RAM, this thing is gonna fly. For a 286, that is. Now there's a couple other things about this motherboard that I want to investigate, and if this memory expansion goes well, then maybe we'll get there. You notice here there's space for a crystal oscillator and it's not populated. The chipset datasheet seemed to indicate that you can use this to run the CPU clock, or you can use this master oscillator here, and this thing does some division and multiplication or whatever of the clock signal to generate the 24 megahertz that this 12 megahertz CPU needs. But if we could switch over to using this oscillator, that's actually better because that would allow me to be more flexible with the speed. And if we install a faster oscillator, maybe we can overclock this thing a little bit. The chipset is only spec'd to run at 12.5 megahertz, and this is 12 megahertz CPU, so it's pretty much at the limit right here, but you never know. Maybe this thing can run a little bit faster and we get a little bit more speed out of it, and having this oscillator on here will give us that flexibility. As far as the slot goes, you can see here it is busted, and I think someone just yanked a card out of this thing very rudely. Now it's possible just a little bit of glue is all that's necessary to get this thing back together, but these contacts are in kind of rough shape as well, but I wouldn't be surprised if I can just kind of bend them back once I glue this together. Worst case scenario though, I could remove this entire slot, and it is an entire single unit here, and either install another 8-bit slot like this one, or install a full 16-bit slot. Now I don't have any of those. Well, I don't have brand new ones, but what I do have is a bunch of dead motherboards I can salvage that off of. I'm pretty confident though that I can fix this with a little glue and a clamp, and then I'll just bend these pins back and then that should work. These are SIPs right here, and if you're not familiar with them, well, you can kind of tell what's going on here. It's just a 30-pin memory module that has some pins soldered onto it, and then you stick them into these slots. I think what was going on at the time when these were out, and that was sort of the late 80s into the early 90s, is I think it was a cost-saving thing. But you can tell by looking at this, they obviously designed this with SIMM sockets in mind. There are the alignment holes right here. Well, they're only on one side, which is kind of odd. That's pin 1, that's pin 30, and it's the same over here on these two slots. And for whatever reason, the alignment holes are just here and here. Not sure why they left them off here other than, well, these traces need to run somewhere. That's probably why. Now you might be asking the question, why would I even do this upgrade? Don't I have some SIPs that I can install in here? Well, this motherboard came with these two 256K SIPs, so 512K total. And yes, I do have probably at least 8 megabytes worth of SIPs that would work in this motherboard. But the problem is I don't have a whole ton of these SIPs, and I do have a bunch of motherboards that use them. So if I use up all my stock of SIPs in this motherboard, well, that's going to mean I'm not going to have any SIPs available for those other motherboards if I ever want to use those. Now, I think there's actually a way to take a regular 30-pin memory module, which I do have tons of these, and convert them into SIPs. And I think how that might work is I could take an old 40-pin chip, like a dead one, this one's not, but I could grab one of my dead ones from a dead parts bin and rip all of these flat pins off and hand solder them one by one onto this 30-pin memory module. Now, in case you're not too familiar, these 30-pin memory modules have 30 pins, but there are contacts on both sides, right? You see the little contacts here? But that actually is not two sets of contacts. It's not like there's 60 pins on here. There's just one row from 1 to 30, and what's on the front and the back are actually the same. So you only need to solder these pins onto one side, because it looks like these original SIP pins kind of hook around the PCB and connect to both sides, but that's more for stability probably and strength when putting it in and out of the socket. And soldering these on would probably work. Oh, it'd be so fiddly though, because the alignment, oops, I just dropped that chip. The alignment would be very difficult to get perfect so that you could easily insert it into the socket. These pins seem to have little flat parts that rest up against the edge of the PCB so that when you install these, they're not all crooked. They're already aligned correctly, and then you can just install it into the motherboard. That might be an interesting experiment though, to try to make a SIP, and maybe I would do that on the second channel. Maybe I'll put a video there. But on the other hand, I could see it being very fiddly, and I can't imagine doing that for 8 1 megabyte SIMMs. That just sounds like a ton of work that I don't really want to do. Now, my idea here is that regular SIMM slots will fit on this motherboard because it looks like it was designed to accommodate them. And I happen to have an entire box of new old stock SIMM slots, and I do have all of them. It was an entire full box. I just took some out of there for test fitting on the motherboard here. But yeah, we have an entire package of these unused. So that's one of the reasons why I think this might be a fun thing to try, because I happen to have these already. And maybe if they fit on the motherboard, then we're gonna make this maybe one of the only 286 motherboards in this small form factor that has 8 memory slots and can easily accommodate 8 megabytes. Now, I hear people saying right now, hey, there are 4 megabyte modules in this form factor, and couldn't I install those on here and actually have a full 16 megabytes by only using 4 of these slots? Well, yes, there are 4 megabyte versions of these, and there are even 16 megabyte versions as well, because there are a couple extra address lines on here that allow all that memory to be addressed. But on this system, those lines are not connected. You'll notice that not everything is connected on these SIMM slots, and definitely after reading the data sheet here for the main chipset on here that runs the entire computer, it only supports 1 megabyte modules. So if you're gonna run 16 megabytes on this system, you do need to have a motherboard that has 16 slots on it, which this obviously does not have and has no room for. So we're gonna be stuck with 8 megabytes. But to be honest, for a 286, that is more than enough. Now, if you're familiar with something like the 5170 here, which is the original 286 machine, you could install extra memory in ISA slots, and you weren't really penalized for doing that, like from a performance perspective. But the problem is with the 5170 is it runs at 1 wait state on the motherboard, and the ISA bus typically runs at either 6 or 8 megahertz, depending on how fast your computer is. So the memory you put in a slot, as far as I'm aware, runs at the same speed as what's on the motherboard, which is only 512K at most on that system. So you do have to expand your 5170 using memory on ISA cards, and therefore it's really easy to get up to the maximum of 16 megabytes. Problem is with this motherboard is it's a 0 wait state motherboard. It couldn't run at 1 or 0 wait states, and that results in a very high performance 286 system. So with the RAM on the motherboard running at 0 wait states, if you add extra RAM on an ISA slot, you are then penalized because A, the slots run at a slower speed than the CPU, which is 12 megahertz, and you also have additional wait states that are added because the processor is running at a faster clock speed and it's running at 0 wait states compared to the bus. So you'll get much worse performance using RAM plugged into the ISA slots. So that's why I really want to get this thing into a state where I can just very easily add 8 megabytes right to the motherboard and get that high performance. All right, so when we're talking about adding these types of slots onto the motherboard, one of the main things is they have to fit. And when you have SIPs like this, the pin spacing can be completely arbitrary. And that's because these memory modules are pretty thin. And if you want to cram more memory in, you can just reduce the pitch between the pin strips here. and that would allow you to fit more RAM in there. And I've seen boards like that where you have the SIPs in there and they are really crammed together. Like you might have 4 of them in the space of just these 3 slots. And when you stick them in here, the PCB and the chips are right up against each other. But because there's flexibility when you have these pins, like I'll use a real SIP here, when you push those in there, you actually have some flexibility because this can kind of bend and move around a little bit, and you can easily squeeze all of those into there. But it looks like for this motherboard, as I mentioned with these alignment holes, it seems like they had SIMMs in mind when they designed it, and for whatever reason, they just didn't bother with it. And that is extremely common. I've seen so many of these types of motherboards that are like that, especially in the 286 and 386 era and these inexpensive clone motherboards. They ended up going with these pin strips, probably for cost reasons, because I have a feeling these are cheaper than these by probably a good margin. And even though the SIP memory modules cost more than these regular 30-pin SIMMs, because obviously there's additional work going into making or adding these pins, that's on the consumer, that's on the end user to buy the memory that's going to go on the motherboard. So it reduces the cost of the motherboard while increasing the cost of the memory. If anyone has a recollection from the old days, back in the late 80s and 90s, what the price difference was between a 1 megabyte SIM and a 1 megabyte SIP, I would love to hear it. It probably wasn't huge, but there's obviously labor involved with installing these pins onto what is ostensibly just a regular 30-pin SIM. When I worked in a computer store in 1991, there were definitely motherboards that were being sold in our systems that had SIP slots. I remember the lower end motherboards. I don't really recall the costs of any of that stuff, but my assumption is the memory must have cost more than the ones without the extra pins added on. Now from a fitment perspective, you can see the bottom of these SIM slots, they just have pins on them. And you can actually just put them right into these pin strips. And if the spacing is right between these strips, it will work. Of course, that means that these things will sort of be flopping around a little bit because they're not going to be soldered in. And therefore installing and removing memory modules, well, that could damage the slots, it could pop them out, you know, all sorts of stuff can happen. So I don't think that's an ideal way to install these. When they made this motherboard, these strips here are not really perfectly aligned. They're all a little like bent over and cockeyed. See, like this one looks more bent over than that. And that makes it where getting these in and fitting them together, it doesn't really work. So I think the only way that it's going to be possible to really know for sure if these even fit is to remove this stuff entirely from the board, and these as well. Now when we look over here on this side of the board, there's obviously extra components we have to worry about, like the keyboard jack here and these chips and stuff like that. So I'm just going to place this just loosely into there, and that's about where it goes right there. And we can tell that that is going to fit. Yes. There's plenty of clearance all the way around, and I don't think there's going to be any issues. Now, same for over here. If I put one of these in there, I think that's about how it's going to look right there. So we have the room we need right there as well. And the final test I think we can do is with the alignment holes over here. There are alignment holes on the bottom of these modules, and luckily I can stick these into the alignment holes and they'll hang off the board there. And I can fit them all in there. I just want to make sure that everything fits together. So that's in there properly. Let's get these all turned the right way, or the same way. Yeah, there we go. They're all in there. So that kind of implies that if I remove these pin strips, these slots are going to fit in here perfectly. The only thing I have to worry about is there are 2 sets of pins here, or pegs, and there are only holes on one side. So I'm just going to have to snip off, well, one set of these and then get these into the board the correct way. The other thing I have to consider is I don't know for sure which is pin 1 on these slots here, unless it's actually labeled. It's on the motherboard. There's pin 1 right there. So we can look at one of the modules here. There's pin 1. So that means the modules are all going to face this direction with the chips facing towards the CPU. And what we can do is we can try to get this into the slot, and we can tell that that doesn't go that way. It goes this way right here. So there it is. Oh, there's actually a pin 1 right there on this module. So that tells us that these need to go in this way with the hooks facing away from the CPU. I think I'm getting ahead of myself a little bit though. First thing I need to do is I'm going to remove these pin strips, and then we're going to see what happens. Hopefully that doesn't cause any damage to the board. I don't rip any traces or whatnot. And then we can kind of go from there. Okay, so for removing the pin strips, it shouldn't be too difficult. And one of the good things is I can actually, on the top side, is I can cut them. I can use some snips and just cut them into pieces. So I only need to worry about getting little bits of them out at a time. If you're trying to remove SIMM sockets and preserve them, well, one of the problems is these are all connected together. So you have to take these 60 pins out and make sure every single pin is perfectly clear so you can get these out of the board. What I'm going to do to aid the removal though is I'm going to use hot air on the back side of the board here just to kind of heat it all up. And then I'm going to use the Hakko 301 here to just carefully and slowly work away at all of the pin strips and hopefully get them all out of the board without causing any damage.
Motherboards like this have a thick ground plane and power plane in the middle layers, and that really wicks away a lot of the heat, so it makes desoldering stuff really difficult. The hot air really helps keep the heat in there and get that solder off the pins.
All right, look at that. That came out. No hot air on the top side. That's cool. How about this one though? This one feels more stuck. There we go. Nice. Oh no, I lost a pin. So one of the pins broke off. Obviously that stayed behind in the motherboard. Okay, so the pin that broke off is right there. What I'm going to try to do is use this soldering iron here to loosen it, and I'll grab it with the tweezers here. Okay, I got it. There it is. All right, well, I only did 2 slots, but it wasn't that difficult. It came out pretty easy. I think the hot air really helped out. And I just need to be careful for the, the pins that are holding on like they were there. What I'm going to do is just scrub this a little bit first. So I can just take a look at the traces, and you can see there, everything looks really good. No issues whatsoever. And on the top side, it looks really good as well. I see absolutely nothing wrong. Perfect. Okay, so we know that this is the correct orientation for it to go in, but there's a peg that's sitting in the right hole there. But these ones are going to need to be chopped off. So I'll use my little flush cutters. Oh, that came off very easily. That should be what we need. And there it is. It just fell into place perfectly. It is in there. That's cool. That's gonna work. So let me grab a little bit of this blue tack or white tack or whatever this is. I'm gonna hold this down, and then I will solder in just a couple pins on each end just to make sure that it is aligned correctly, and then I can do the rest. All right, I have a pin in each corner connected, so now I can just remove this. I can hold it down with my fingers and just give it a push, and I'll just reheat these 2 corners. Yep, there we go. And just to double check, there it is installed. And remember, that's pin 1 right there. I mean, I don't have all the pins soldered in, but that would clip right into place, no problem. And obviously we have clearance for both of these to go in properly. And it doesn't even cover up the bank 2 and 3 writing. So that allows you to know that you're installing the SIMMs correctly. Okay, well, next up is, I'm not gonna finish soldering this. Let me just remove all of these. That's gonna take quite a bit of time, and then we'll go from there.
All right, this sequence is going to be a little bit long, so I'm going to do a voiceover. Unfortunately, while I was working on the motherboard, I had some music on in the background. I didn't really think about the fact that you'd be hearing that in a sped up fashion. So I've added some nice jazz music here to make it sound a little bit better. So normally I work on motherboards like Commodore 64s or other 8-bit machines, and those are just 2-layer PCBs. They don't have that center ground plane. So having the extra layers really does make it a little bit more difficult, hence the need for copious amounts of hot air. The other really important thing when you're doing this much work is you have to clean your desoldering gun pretty frequently. I added flux to the pins before I started, and that really sort of gums up the desoldering iron quite a bit more than if you're not using it, but I felt it was still beneficial. And I found turning up the heat on the desoldering iron helped a little bit as well. But that all contributes to just gumming up the whole thing, so I had to clean it pretty frequently. When you're watching this sped up footage here, I did cut out a lot of that cleaning process, but I had to stop periodically because it just wasn't sucking very well. And once I cleaned it, then I'd attack another whole bunch of pins, and then I'd have to do it again and again and again. So So my tactic after finishing the desoldering was to try to wiggle all the pins out of the board that would break any kind of, well, residual solder that was still there, and then hopefully I'd be able to get them out. Now, one of the things that happened is occasionally pins would get stuck, and if I flipped the board around and wiggled, I could see the pins that were stuck, and then I would try to desolder those a little bit better with the desoldering iron, and then repeat and repeat and repeat. Now, I did end up breaking some pins, which I'll talk about in a moment, but that was just par for the course. And, you know, to be honest, I wasn't trying to save these pin strips, so it didn't really matter. Now, installing the SIMM slots was pretty easy. I was so relieved that they just fit right on the motherboard. All I had to do was trim that extra peg off one side, and there we go. Everything went in really well. And then it was just a matter of soldering all the pins so that the SIMM sockets would be in the motherboard nice and secure, and keep my fingers crossed that everything would work. The footage you're watching here is sped up around 10 times, so you can think about the fact that this footage here is several minutes long, multiply that by 10, and then of course I did cut out some of the cleaning and a little bit of stuff that's happening in between. So this process was definitely time consuming, but I think in the end it's still going to be worth it. That's of course if it actually works. It's very easy to damage the motherboard by lifting a tray, so you need to be pretty careful when getting out the pin strips. You don't want to force anything. They should come out pretty easily, and I did inspect pretty closely after they were out just to make sure that there were no rip traces. And all we have now is a little bit of cleaning, and then we're done.
All right, well, that was a good amount of work, but look at that. All the SIMM sockets are installed in the motherboard. Everything is soldered in, and I think we're ready for some testing. The removal process wasn't too hard. I had to just take my time, work methodically, clean the desoldering iron frequently. I did break a few of the pins. There's one there that's broken. Yep. This one has no brokens. Another one broken on that one. This one has 2 broken on it, 2 pins broken. That one's fine, that one's fine, and that one has a broken pin. So I broke 5 pins off on these, no big deal. It didn't damage the board at all. Everything under here looks pretty good with the SIMMs installed. There's still some sticky flux residue, so I'll have to clean that up a little bit more. But you can see the pegs are in the holes there, and over here, the pegs are in the holes there. Looks good. Now, the funny thing is, I ran out of solder while I was doing this. This is the stuff I normally use, this Kester stuff, and I ran out, and I thought I had more. But when I went to open the roll, it turned out I had this microfine hair stuff. So this is not really useful. I'm gonna have to order another roll of this. I thought this was actually gonna be usable, but it's not. It's way, way too thin. And the worst thing is I have 2 more rolls. So these 3 rolls were given to me. So I didn't pay for these. I just looked at the top and thought, oh, those are gonna work for me. So I didn't reorder the stuff that I normally use. And then I ran out. All right, well, let's get some RAM in this thing. And I really, really hope it still works. I'm just gonna start with 2 1 meg SIMMs. I've never tested these, so I don't know if they work. The way the RAM gets installed in a board like this, you have to start with bank 0, 1, 2, you know, so on. So we're gonna use bank 0, which is this socket and that socket. Look at that, easy peasy. RAM just went in. That was great. Oh, one little note while I was at it, I went ahead and I cleared out all the holes for the crystal oscillator here, and then I installed the bypass cap here and those pins there. There's a jumper there and there, which I assume have something to do with the crystal oscillator, plus these 2 resistors. And before I install the pins for the jumpers, I'll just Dremel through these 2 lines there, but I'll leave this until after we make sure the board works with this RAM. Okay, power supply is connected. The post analyzer card is installed. Let's tilt this up so you can see it. And let's power this up. Excellent, it's still posting. Phew, I am relieved. I am freaking relieved. So let's get a video card in this thing so we can make sure that it's counting up 2 megs of RAM here. Believe it or not, this is my first time ever installing SIMM sockets onto a motherboard. I've wanted to, well, figure out the right way to do it so I could try to change some that have the broken clips on them. And now I think I'm confident enough to do it. But here we are, let's turn this on and let's see what happens. Okay, it's counting up memory. Nice. that worked. So 640 plus 384 plus 1024 is 2 megabytes. Excellent. Let's keep going with the RAM here and install more of it. So one of the issues with these SIMM sockets is they're pretty close together. So that means that when you're trying to fully populate the banks here, you need to do a little bit of rearranging to get the memory in. Okay, so we should have 4 megabytes of memory now. Here we go. Let's turn this on. Gave us a beep. Now, we could have bad memory, by the way. I don't know about the quality of this RAM here. I'm just going to take out one of these SIMMs. Yep, still unhappy. I did rearrange that first bank there. So we're back to just bank 0 here. Okay, I guess one of these memory modules is bad. Right, must be that one right there. Because I think I had one of these two in there as the original bank 0. Yeah, it's posting now. So this SIMM here gets an X on it. Not surprised. This stuff was just random in a bag of parts. Okay, actually, you know what I want to do now? I'm going to take all this memory out, and just for fun, let's install some 4 megabyte modules in here, and let's just see what happens. Even though this has 8 megs in here, my assumption is it's going to count up exactly 2 megabytes of RAM. So I power this on. It's posting. It's a good sign. But yeah, it's definitely not going to see it. Yeah, so that sees it as a weird amount of memory, even less than 2 megabytes actually, instead of 8 megabytes. Anyhow, just like I thought, it doesn't support 4 megabyte modules in any kind of way other than just 1 megabyte because it doesn't have those extra address lines. All right, I have 4 megabytes of memory installed in the computer. What's it gonna do? Is it going to work? It's posting. Should have much more extended memory now. We should have 3 megabytes of extended memory, and we do. 4 megabytes, awesome. I now have 6 megs of RAM by installing RAM into bank 2, which are these two SIMMs right here, and this is bank 3. Yep, there it is, 6 megabytes of RAM. And there we have it, 8 megabytes of RAM installed in the 286. One thing I'm noticing, by the way, is the original RAM that I was trying to use, 120 nanoseconds. Pretty slow stuff. Everything else I've been installing in this board, all the rest of this memory here, is a lot faster, but I have 2 of these installed in the board right now. That could cause a problem, I suppose, when we try to overclock this thing. All right, here we go. 8 megabytes, are you gonna work? This is so cool. I don't think I've ever had a 286 board that could accept 8 megs of RAM right on the motherboard. It's really more memory than you really need for a 286, but it's just cool to say you have it. Yeah, there we go. 8 freaking megabytes of memory. Oh man, that is so darn cool. I have a great feeling of satisfaction right now knowing that just removing these pins, which wasn't really that hard, and putting in SIMM sockets was all it took to get me an 8 megabyte 286 board that, you know, and these sockets are really high quality, by the way. The SIMMs go in really easily. It's not hard like the Macintosh ones. They come out very easily as well. And yeah, it's pretty awesome to know I have a 286 board that can accept up to 8 megs of RAM. That is so cool. It's a bit of a shame it can't use these 4 meg SIMMs. Maybe there's, you know, it'd be pretty funny if that extra address line was there on the main chip and I just needed to wire it up, but I don't think it would be. It was very explicit that it only supported 1 meg modules. Okay, so for now, I'm gonna cut the power on this thing. I think for the memory side of things, I need to do some more, you know, tests on this thing, let it run through full RAM tests and stuff like that. You can't run mem test on a 286, so I'll have to use something like Check It to do that RAM test. But that is just so cool to know that that freaking worked. The RAM, I just love seeing a bunch of SIMMs on a 286 board. Okay, well, let's try to sort out this little area right here with this clock crystal. I don't know if this is actually wired up to the chip already, but I have a feeling it might be based on the 2 jumpers here. So for me, when I want to cut through traces, I now use this, which is a little engraving tool. It just is so much easier than doing it with a knife, because then it's difficult to make sure you're right on target and you don't cut something you don't intend to. So I'm just going to cut through these. Once you've done that little operation, you need to make sure that there's no continuity anymore. So that one is good. and that one is good. So excellent. It's interesting how C62 is not installed. Okay, strangely enough, it doesn't have any traces running to it on the top or bottom side of the board. This is definitely a multi-layer board, but I think in the middle layers, it's just ground and 5 volts. It doesn't have any actual traces. It doesn't appear to have any traces. If there are traces, you can usually see them running below the board, like see around this hole here. You see there's a little bit of a color there. I don't think there's anything actually running under the top layer here, or the bottom layer on the other side. All right, the jumper pins are installed, and I went ahead and installed 2 additional 4.7K resistors into those positions. Those are definitely like resistors that are handling the signals that go through those jumpers. Also, poking around on the signals here, I don't think this jumper, JP5, has anything to do with the crystal oscillator. One side of this is connected to ground, and the other side goes to this side of the resistor, and this side is on 5 volts. And that signal on the bottom of the board goes up to a via over here somewhere. And it seems that when there was an actual wire or trace between these 2 pins, what was happening is that signal was always being pulled to ground. But now with this jumper removed, it's actually going to be pulled up to 5 volts. Reinstalling the jumper brings it down to ground, just like it was when, before I did the mod. And then the other resistor here does have something to do with the output of the crystal oscillator. And it seems that the signal goes to there, and then it goes over here somewhere, and I don't know, off to some other part of the board. This jumper here, which was not installed, remember it was connected between these 2 pins right here. That side goes to that side of that bypass cap, which is, obviously that's 5 volts. The middle pin and this pin, the ones that were connected, they kind of go off somewhere else on the board. Well, the middle pin actually ends up right here, and I think this is what, the ROM chip? And that one there goes up somewhere else on the board. I wonder if it's something to do with the size of the EPROM. So yeah, the middle pin goes to this pin, pin 1 on the ROM chip there. Don't know what kind of, or what size ROM chip this is. It says even, but that's ridiculous. There's only one of these chips here. So it actually has the entire ROM inside of that EPROM. Now, pin 1 on typical EPROMs, if this is like a 27C256, I could feel it has a window underneath there. That's the VPP pin, and typically you just pull that up to 5 volts when you're not programming the chip, that is. I'm wondering if this thing supports some type of EPROM programming, maybe with an EEPROM. I'm not totally sure. But the reality is I would expect that that should be always pulled up to 5 volts when the system is running. But the reality is this pin right here, the one that's not connected to that pin, that's the 5 volt pin. So I don't know what these are doing. Yeah, interesting. But that pin there, I can see it has, it goes up here to like one of these vias up here, which they kind of look like they end up at the main chipset. And probing around on the chip here, there it is. It's connected over to this. So that's weird. I don't quite get what that's doing. Let me just install some jumpers on here before I forget. Like that, the original configuration. Now for the crystal oscillator output, it ends up going through this resistor here. And it might not be a 4.7K. I should put like a 20 ohm or something there. I wonder if this makes its way over here to the main chip. So let's see. 29 ohms. Interesting. All right, I'm going to install an oscillator in here. I'm going to install a 24 megahertz one, or maybe I should install a slower one. Yeah, let's do that, because in case we want to see if this thing is running at some kind of a slower speed by manipulating some of the registers at least. Okay, powering on the computer, it is posting. We only see 512 megs of RAM though. That could be because the CMOS is unhappy. I need to get a keyboard. Actually, just power cycle the computer altogether. Yeah, interesting on that first power up, when the CMOS is corrupted, it doesn't count up all the memory. Now, one of the things that I'm worried about is that the crystal oscillator is running right now. It's outputting 8 megahertz, and I think it's going into pin 1 of the main chip here, but I'm going through a 4.7K resistor, which may be, well, too much. It's 24 megahertz on that signal here on the resistor. On one side of it, it's 8 megahertz, and on the other side is 24 megahertz. So it seems like something else on the motherboard is actually generating the clock. So if I remove that, yeah, there we have it, 24 megahertz. That's the CPU's clock right now. Oh, I feel so absolutely silly here with this whole thing I was doing down there. I think all of that was just for nothing. Luckily, it wasn't really much time wasted. And the reason why is, take a look at this. There it is, 24 megahertz. There's the crystal oscillator down there, oscillator 1. That is what's generating the CPU clock. And it looks like I can just remove that from the board and then install, well, some pins just like these down in there. And then I can stick the oscillator down there. Now look, there's a space for oscillator 2 as well. Interesting. I don't know what oscillator 2 does exactly, but oscillator 1 is the relevant one that we need to do some overclocking of this system. Okay, that was pretty easy. There it is. The oscillator is out of the board. Just fell right out, actually. And here is why they use that small package. Because the regular size ones don't fit. That is pretty hilarious. Now what I'm curious about is down here, we actually saw the 24 megahertz. Does that mean we have a replica of oscillator 1 down in this lower area here? That's not a connected pin. That has continuity. And then this is the signal pin here, which doesn't have continuity immediately, but I wonder if we have it over here. Well, it doesn't appear that these two things are connected, but what I can do is just simply remove this resistor and add a bodge wire from the signal wire here to there. So we can put an oscillator here because the 5 volts and the ground is correct, and then the signal will just be routed to the signal pin there, which obviously makes its way probably through a buffer or something before it gets to this. Okay, so the resistor is removed. All right, I have a little bodge wire installed. It goes from the signal output pin for the crystal down here, and it goes into where the original output pin was on that oscillator. Okay, so everything's reconnected except I don't have an oscillator installed. So when I power this thing on, we're gonna get nothing. Yeah, we got nothing, just dashes on the postcard. All right, let's pop in this 8 megahertz oscillator into there and see what we get. Okay, it's posting. It's gonna post slowly. It's working though, that's pretty awesome. So the cool thing is now is I can just use standard metal oscillators, and I have a whole bunch, including one at 24.5 megahertz, so that's a slight overclock. And then I also have a 28 megahertz one here, which will be a little bit more of an overclock. We'll see how far we can push this thing. Now there are faster CPUs in this package. Harris makes 20 and 25 megahertz parts. Pretty sure I have both. But I think the limit of the speed of this computer is going to be the main chipset, which is only good for about 12.5 megahertz according to the datasheet at least. It's funny, it said keyboard error. Did I damage the keyboard somehow? What I'm going to do is I'm just going to reinstall the original 24 megahertz oscillator in here. That way I can rule out any other weird issues with speed and stuff, like causing the keyboard not to work. I have the original 24 megahertz crystal back in the motherboard. I think this should fix the keyboard problem. Keyboard is working now with the system running at the original 12 megahertz, but with the 8 megahertz crystal back in here, which runs the system at 4 megahertz, divides it by 2, keyboard's not working again. And I can't, for instance, go into the CMOS setup. So there must be something with the keyboard controller. Maybe it doesn't like to run at that slow of a speed. I'm actually not sure what clock speed the controller runs at. All right, so you can tell that I've rearranged the RAM a little bit. What happened is I took out the slow memory that I was originally using. I think it was this stuff right here, 120 nanoseconds. And that's because I want to try a little bit of overclocking with this system. I'm not going to change anything. We're going to use this original AMD CPU here. Let's start by installing this crystal oscillator here. This is going to run the system at around 12.2 something megahertz, which is only going to be the slightest overclock. Now in the CMOS setup here, one of the things I found is I did a little bit of testing off camera last night where I checked to see if this refresh stuff makes any difference whatsoever. And it does seem to make the slightest of difference. My thought is that this particular setting controls how often the DRAM is refreshed. Now I know the value that is used on the original PC and the PC XT and the PC AT is very conservative. And I know you can slow it way down without any kind of instability issues, but that is gonna vary by what kind of chips or DRAM you have in there. And some DRAM is gonna require more refreshing than others. Now, if you're not familiar with what I'm talking about with refresh, DRAM requires periodic refreshing or accessing of the memory in order for the contents to not degrade. You have to think about each little bit of memory in here as a capacitor, and capacitors don't hold their charge forever. They slowly decay away. So the way the circuits are set up inside these DRAM chips, when the chip is accessed, it actually reads back a value from the capacitor that's in there and then writes it back, which essentially refreshes it. So the refresh interval is how often you need to go through and do that process through all of the DRAM. And on a PC, it uses a DMA controller to do this refreshing. So you set up the interval timer. That's one of the support chips on the PC. Of course, it's built into the main chipset on this one. And then that triggers the DMA circuit to go through and read all the DRAM. And that means that, yes, it's taking away some of the DRAM bandwidth from the CPU. So if you could turn off the refresh entirely and use, say, static RAM, which doesn't require refreshing, I think you can get something like a 16% boost in RAM performance. So slowing down the refresh interval so it doesn't happen as often will give you small boosts of memory as well. And I've never actually found a BIOS that has a refresh interval that is controllable, and it seems that this BIOS does. Now, from my very limited testing, because I don't have a full test suite available to check for RAM throughput, I think 140 nanoseconds here is the best selection. Let's go do a little quick test here to see if our little miniature overclock worked and what the RAM bandwidth is. In speed 600 here, we have 12.329 megahertz is registered now, and we're getting 19.08 effective megahertz. That's a relative number that's only useful for this particular test. With the original oscillator in there, I think we were getting about 12.0 something megahertz and 18.5 or 18.6 megahertz on the speed 600 effective CPU speed. Let's use vid speed to do a RAM throughput test, and if you just use the asterisk here, 7878 bytes per millisecond. And that's with it set to 140 nanoseconds for the width. Let's go to the other extreme and do 350. Oh, incidentally, it says chip SCAT BIOS at the top there, and reading the datasheet, it tells us that SCAT stands for single chip AT, which was Chips and Technology's design goal, I guess, of getting everything that's on the motherboard of the 5170 down to a single chip. Pretty amazing they were able to do that by 1989 when the original PC 5150 came out in what, 1984, I think? Okay, so here we go. I'm going to run vid speed. Remember we got 7878 before? And what are we going to get now? 7761. So there's a slight improvement. And in case you're wondering, if you run this multiple times, you do get the same exact number every single time. So the improvement is slight, but it's there. 7878 versus 7761. Now what I find interesting is my initial assumption was that this particular value talked about how often the refresh was happening. So 350 nanoseconds, every 350 nanoseconds. That doesn't seem to be the case. This seems to be something to do with how long the refresh cycle takes. I'm not 100% sure, but all I can tell you is that we do have an improvement setting it to 140 nanoseconds. All right, so our processor overclock does work. Now here's an interesting little tidbit inside of this thing. You can actually control the speed of the CPU inside the BIOS here. And oddly enough, CPU X1 means that it's going to be running at half of the crystal oscillator speed, so a little over 12 megahertz in this case. But we can run it at half of that speed, or a quarter, or even an eighth. I don't know why it would offer such wide-ranging options here, but let's save this set to eighth, and theoretically we should have a very, very slow 286 system now without even changing the oscillator. I don't really see the purpose of having such a wide range of dividers. And here the system is running at 2.1 megahertz at the moment, which is really slow, far slower than if you take off the jumper, which when you take off the turbo jumper, you end up at 6 megahertz or so. Let's see what happens when we take off the turbo jumper now. It slowed it down even further. Let's retest here to see what the new clock speed is. Unlike later systems that just add wait states and things, this thing seems to actually alter the clock speed by taking the turbo jumper off. I kind of assume we're going to be running around 1.2 megahertz now. 1.22 megahertz. That is so unbelievably slow. Wow. Kind of cool though. That gives us an interesting test bed for seeing how slow we can run the system. Remember, when I tried to run the system at 4 megahertz using this 8 megahertz crystal oscillator, the keyboard controller didn't work. But what seems to be happening here is that the chipset is only driving the CPU at this far slower speed, but probably the rest of the components are still running at a decent clip. How about we do a benchmark and check it to see if a 1.24 megahertz 286 is just as fast as an XT. I think it's going to be slower. I think an XT is like 500 dry stones or so. Yeah, 0.72 times the speed of an IBM XT right now. I'm going to reinstall the turbo jumper and we'll run that again. So now we're at that 2.15 blistering speed. And I think we're actually faster than an IBM PC XT or the original PC now at 2.15 megahertz. Now, why do you think this machine is faster at 2.15 megahertz than something like an XT? Well, there's a few different reasons. One of them is that this is a true 16-bit processor and it doesn't use multiplex address and data lines. Those are actual individual pins on the CPU package. That means you're not waiting for latches to latch in address lines and data lines separately, which is what's happening on the 8086 and the 8088. In addition, the instructions that run in the 286 are more efficient than the 8088 and 8086. They run in less clock cycles, and therefore you're actually getting a nice speed improvement even at this lower speed. So that's why I think in this benchmark, we're running at 1.29 times the XT's performance, and we're running at less than half the clock speed. Now, here's an interesting thought. All of the stuff that you set up in the BIOS is actually controlled through registers in the chipset. And it's quite possible to control those registers in DOS using like a little tiny DOS program. Therefore, it's totally doable to actually change the clock speed on this motherboard on the fly. And we can change it at all those different intervals, which would make this motherboard really good at running really old programs that are too fast, even on a 286. And there are some stuff that really doesn't even run properly on a 286 because it was really designed with the XT in mind. Now, it's too bad there's no granularity available to us for really fine control of the clock speed inside of DOS, but nonetheless, it's still pretty cool that this is technically possible. Now, when I first showed off this motherboard on the second channel, we saw that there's actually direct register control in the BIOS here of all of the registers that are in the chipset. But what I didn't do is I didn't explore the options. I didn't explore what we saw here. All you see when you go in here is just says reserved bit. But I realize now that you can actually scroll through every single option and it enumerates exactly every single option. And I checked against the datasheet for the chipset and everything in here matches exactly what's in the datasheet. There's nothing in the datasheet that's not in here or vice versa. So in here, we can control the 16-bit DMA wait states, the 8-bit DMA wait states, and they're both set to 1, which is the fastest possible. There's this DMA extended feature here. It does explain it a little bit more in the chipset manual. You can control the DMA clock speed, which is an option available on a different page here. I think it is right here, CPU X 1/4. And if we go back to here, there it is, CPU X 1/4. And if you change it on the other page, it changes it in here. But you can change it on either place. Here's an option called Quick Mode Enable. This has something to do with the address latch enable. And it seems to be an option to speed up the system on very slow clock speed systems. I do know that if I turn this on, it will make the system not post anymore if it's running at full 12 megahertz. Here's the bus speed clock select, and it looks like normally it's taking the CPU clock, which is 24 megahertz, that's pro clock, and dividing that by 4. So that ends up at a 6 megahertz ISA bus, which is actually a bit slower. Pretty much everything will work perfectly at 8 megahertz, but most cards work fine at 10 megahertz as well. But putting it to /2 makes the ISA bus run at 12 megahertz, which is a little bit out of spec for some stuff. And I can confirm I did test this off camera, that if I run the system at 12 megahertz and I set this to pro clock /2, the system is posting, but for whatever reason, the compact flash card on my IDE card doesn't work anymore. So it's a little bit too fast for that particular card. The datasheet, though, has a diagram explaining how the entire clock circuitry works. So frequency source, so that's the crystal oscillator, which in this case is what, 24 and a little bit megahertz. The output of probably what is the chipset, which I think would be this box right here, ends up as various clock signals, including pro clock, which is what goes to the CPU itself, and that's 24 megahertz in this case. So for the bus clock, which is the AT ISA bus speed, it looks like it's just pro clock divided by 2 or divided by 4. Here's the refresh command pulse width. This is what we were talking about for that DMA refresh. The next few things have to do with stuff on the XD or SD bus. And I think what SD bus is more like the ISA bus, and the XD bus is some internal local bus to do with the chipset. And that would have to be onboard peripherals that this chipset can somehow interface with. So everything here just needs to stay as SD bus. Sleep mode enabled or disabled. Don't know what this is all about, but it does look like you can halt the CPU in some kind of a sleep mode. Not sure how you wake it up from that sleep mode though, so who knows. You can turn off parity checking for the RAM. And I read the manual and it says that this setting is ORed with another setting that's just used in a standard IO port on the original 5170. It had it as well. You could turn off parity checking. So either this or the other setting will disable parity checking, so it will not generate non-maskable interrupts. If you're using SIMMs that do not have the extra chip on there, so they have either 8 chips on this type or they have 2 chips on this type, then you need to turn off the parity checking. It's fine that it's on, it doesn't really slow anything down, but if you're getting parity errors because you're missing those chips, you can just turn that off. CPU frequency select, so that's what we have set to 1/8 right now. There's the sleep frequency. High level DC means it's going to halt your CPU altogether, or I guess you can slow down the CPU on the fly using this sleep mode. I don't know how you wake it out of the sleep mode though to go back to normal speed. Next up, we have the ROM enable register. Now, it seems that the ROM enable line or the chip select line that comes from the chipset, this is to go to the motherboard ROM chip for the BIOS, right? It actually allows you to have a much bigger ROM than just this one here, which I'm assuming is a 27512 because it has that extra address line going to pin 1. So the way this works is you could see on the left side there, we currently have a 1 under bit 7 and bit 6. And when you look at bit 7 and bit 6 in the little range there with the addresses, you'll notice that we currently are turning on the ROM from F0000 all the way through FFFFF. That's that top 16K of BIOS ROM, which of course maps to the 27512K chip here. What's cool though, is if we put in a larger chip, say we put in one that had extra address lines, it wouldn't really fit on this motherboard, but we could wire it in. We can actually add another 16K of ROM by enabling bits 4 and 5, and that would select the ROM from E0000 all the way through FFFFF. So it's pretty cool. You can actually select where the ROM is enabled. And I think the reason why they did this is because motherboards that have onboard peripherals, like imagine a VGA adapter or a disk controller or something, you wanted to have your own ROM, you would add that into the EPROM, and then you could enable these chip enable lines here in the registers. Quite clever. Next thing you can do is you can write protect the RAM in those upper ranges. This is in the above 640K. The purpose for this, if you wanted to do a shadow RAM, like you wanted to copy the slow ROM off the motherboard into the main system RAM, you would do that, and then you would enable the right bit here to write protect that RAM so that the system running can never change the value of the ROM that's sitting in RAM. That's a typical strategy used on 386s. It's a little less common on these types of systems. The reason why you want to do that is because the RAM is really fast on this system. It's 0 wait state, 16-bit, but the ROM, as an example, the BIOS ROM is an 8-bit ROM, which means it's accessed very slowly because it has to do 2 accesses for every 1 address. So the shadow RAM, which I've enabled for both the system BIOS but also the VGA card, copies the ROM off the VGA card and the motherboard into the RAM, and then I'm assuming once the system boots up, it write protects it. Like copying the slow ROM on this 8-bit XT IDE card into RAM, then you would write protect it. And in fact, the very next register is shadow RAM register, and this allows you to designate that you want those accesses, instead of going to the ISA bus to read off this ROM card, you want it to go directly to the system RAM. And there's a bunch of registers here that gives you all the various addresses. And then we have another set here, shadow RAM register 2, and shadow RAM register 3. That encompasses the entire upper 640K or upper 384K of memory. Next up, we have DRAM timing, which is a setting we have in the regular BIOS anyways, but we have a few different settings there. It's interesting that it's using 3 bits to determine this, but yet there's only 3 possible values when we actually have 8 possible values. And I wonder what those other configurations do. Maybe they're additional wait states, like 2 or 3 wait states, or I don't know actually. And then the next register here has to do with how much RAM you have. This is also something we could just set in the regular BIOS. We have RAS encode, disable, or enable. This is to enable 16 megabytes of RAM on the motherboard if you have 16 slots. You add an extra 3 to 8 decoder, and that gives you access to 8 banks of memory instead of just the 4 we have right now. You can disable DRAM in certain ranges of the address space. Not sure why you'd want to do that. You can create an upper memory boundary, and I think the reason for this is, say we have 8 megs of RAM, but you only want to have 4 megabytes of main memory and extended memory, and then you want to use EMS or expanded memory. I think that's expanded memory for the rest. So you would set a boundary to 4 megabytes, and that would keep the other 4 megabytes free and invisible from the regular, DOS software like HiMemSys, and then the EMS driver would be able to use that extra 4 megabytes. And then we have the settings for enabling and disabling EMS, but this stuff is all available in the regular BIOS stuff. Now, of course, there's a bunch of reserve bits. Who knows what those do, right? I mean, it lets us tweak them, I think, does it? Yeah, you can change these reserve bits. Who knows what they do, but maybe there's some hidden and awesome features available in this chipset that, can be exposed by tweaking some of those reserve bits. All right, for our next crystal, 28.322 megahertz. That should give us around 14 megahertz. If it's able to be stable at that speed. And that is a very hot CPU there. So it's definitely, these run quite warm. All right, system is posting, great sign. The bus speed will have sped up a little bit as well, because remember, it's running at divide by 4, so 28 megahertz divided by 4. So we're now at like 7 point something megahertz versus the 6. All right, so video speed sped up. It was 1630 last time, and now we're at 21.93 megahertz with a CPU clock speed of 14.212 megahertz. Let's see what our RAM speed is. 9100 bytes per millisecond. Pretty speedy. That's awesome. Running Jim Leonard's top bench. I'll just hit pause there. So mem test 429 microseconds. Lower is better. This example system here is at 286 at 16 megahertz, so a little bit faster clock speed. It does have a faster memory speed than we get, but we're only running at 14 megahertz. So I'm assuming that that system has 0 wait state RAM as well. But then MEA, whatever that is, we are actually running faster at 208 versus 241. Opcodes, which is more to do with CPU speed, we're running at 165 and it's 197. And then the video memory is a little bit faster on that system, but it has a Sang ET3000 versus this junky Cirrus Logic card. 3D games is the same, and the total is roughly the same. So that's pretty cool that we're competitive with the 16 megahertz 286, even though we're only running around 14 megahertz, and we're overclocking this 12 megahertz chip to that 14 megahertz. Now I'm curious, if I set it to CPU 1/2 and we hit F10, that should run the system now at about 7 point something megahertz. And that's corroborated by what we see in speed 600. Now if I remove the turbo jumper, it looks like it froze the system. It did. The whole computer's just frozen. It was working when we had it running at 2 megahertz. I just put the jumper back on, but now the system froze. Let's reboot the computer. Hopefully it's still running at 6 megahertz. What I want to try here is, now that this is running at a slower speed for the CPU, I want to try an even faster crystal oscillator here. And let's see if that results in a working system. All right, just double checking that we're still running at 7.45 megahertz. That's with the turbo jumper installed. So I have a 32 megahertz crystal, which would normally result in 16 megahertz, which is a bit of an overclock for the system. But with this in there now, if all things work, we should have 8 megahertz. And I suppose we can try overclocking the system to 16 just to see what that does. System is posting. Excellent. And the RAM isn't working. And I'm wondering if that's because the system clock is running too quickly now. Oh yeah, the post is just frozen at 1. It's posting now after a power cycle. Ah, no, it's just hung. All right, well that seems too fast for something. Go back to the 28 megahertz crystal where it was running. And maybe what I should do is put a wait state in there. And with a wait state, oh, well, now it's gone back to its defaults anyways. So we'll leave it at slow, which I guess is the same thing as divided by 2. And then I'll add 1 wait state in. And let's see if we can make the system work now. So 32 megahertz crystals back on the board. See if we can get a post and have it not freeze. Nope, it froze again. So my feeling is we're running up against the internal clock divider. On the diagram for the clocks we looked at earlier, there was one that kind of went off and it was like for internal use, and it's based on the crystal, the external crystal. So I guess we're pushing the chipset a bit too far. The internal functions of the chip just aren't running properly, even though the CPU speed is well within limits at 8 megahertz. So 28 megahertz crystals back in there because the system is nice and stable with that at least. Okay, so from a clock speed and performance perspective, I think we're pretty much maxed this system out. We can support 8 megabytes of RAM. What we haven't really delved into is what changing these jumpers do exactly. I'm positive that this one is going to disable this extra address line on the EPROM here, which will make the system not work. So let's just switch it over to the other setting. Yep, it's not posting. I don't think it will post now. No post. And that's happening for a very specific reason. On Intel processors, when you first turn them on, they actually jump to the very top of memory, and that's where they look for their initial jump instructions to begin executing the ROM code. Well, since the EPROM here is a 27512, and now since that jumper's changed, that top address line for the EPROM is now just at 5 volts all the time. That means the lower half of the chip from F0000 to F7000, whatever, can't be seen. All it sees is the top half. Probably what happens when it goes to that first instruction is a jump instruction. It ends up down in the bottom half of the EPROM, although that's gone. So what happens is it just has a mirror of the top half, and it's just gonna run some code that doesn't make sense, and the system is just gonna crash. So the original function of that jumper is to set a half-size EPROM, which of course there's no need for that on a system like this because this is a 27512. So setting that back to its original configuration, yeah, the system is posting properly now. Now this other jumper here, I don't think I fully understand what this could do. So let's take this off. The original configuration was with it installed. And if we turn on the system, it's not posting. What that does, I don't know what that does exactly, but it results in the system not working anymore. Now with this back in its original configuration, here's an interesting thing I want to try. So we'll let the system post here, and you see I have BIOS shadowing turned on. I think what's going to happen is if I let the system boot up here into DOS, I can actually take the jumper off for the ROM and it will have no effect. And that's because it's now running the entire code for the BIOS out of the DRAM. So let's just swap this over. So there we go, it's swapped over, and yeah, the system is still working perfectly. Now it's working for now, but if I hit Control-Delete, it will fail at that point. So Control-Delete, and yep, system is just dead frozen. And that's because it probably resets the registers inside the chipset here, and then it goes back to the ROM to try to read it, and then that's bad, and then the system is just dead. Okay, I just went and dumped the system ROM. That's in case that's not available on the retro web. I'll upload the ROM to there if it's not. This is Jim Leonard's ROM dumper utility. It's very useful. I use this all the time. Works great on older systems like this for dumping any of the ROMs that are available, so you don't even have to remove the chip, which of course is dangerous because you can put it in backwards and then destroy it. So I always use this utility. It's much safer. All right, I think at this point I've done all the exploration there is to do on this system. I've kind of done all the mods and things I want to do. All we have left to do is try to fix this slot here. So my idea is getting a little bit of glue to try to hold the plastic slot cover together. But obviously these pins are bent. I don't think that's going to be that much of a problem, because I think a little bit of bending might be able to recover this, maybe. It's not, oh, that's too much. You can see it should be pushed up against the stop there. There's a little bit of a lip, and these are definitely not doing that. So this may not actually work. And the reason why is because when someone yanked the card out, they actually overbent these pins. They're kind of curved and they bent on the bottom side down below. And when the card was yanked out, the plastic moved over far enough that these were able to bend and overextend. And that sort of permanently bent them. And I'm just trying to poke them down below. It's a bit better. It's a little bit better. Let's see what happens when we stick a card in there. So I'm still obviously holding the slot there. Let's see if these are pushed up against the card. They seem to be pushed up against it. Well, I have the power connected. Let's turn this on and see if we have a functional postcard. Yeah, it's working. Okay, I think that did the trick. I just need to glue the slot back together.
And a little CA glue hopefully does the trick.
So there it is. An awesome 286 motherboard running with a slight overclock at 14.5 megahertz or so, with 8 megabytes of SIMM memory on board, upgraded from the SIPs, which I much prefer the SIMMs here, and that was actually a pretty easy upgrade. So I think now I'm confident enough to try to replace broken slots on other motherboards, and I do have some, with these new replacement SIMM sockets. So if you enjoyed this little exploration of this awesome 286 motherboard, I'd appreciate a thumbs up. If you didn't know what to do, huge thanks to my patrons. Their names are scrolling up the side of the screen. Hit that subscribe button if you haven't already, all the usual YouTube junk, and that is gonna be that. So stay healthy, stay safe. I'll see you next time. Bye.